Alright, hello and welcome to another episode of How to Understand X. Today we're going to be tackling the integration. It is a little bit late, so I'm going to have to probably split this into two halves. But I do at least want to talk about the formal definition of the integral, definite integrals, a proof of the fundamental theorem of calculus, then maybe U sub, tabular integration, just, some important ideas. And then in the next video, we're going to have improper integrals, and we're going to do some weird stuff in the latter half of this. But let's talk about the integral. Now, in calculus, we know that differentiation, or the derivative, is going to be our most important operation. Differentiation is how we find the instantaneous rate of change, or the slope of a tangent line of any given function. But what is the inverse? We know that differentiation is an operation, right? We can differentiate both sides of an equation. We can do something with differentiation. And, multiplication has division. Addition has subtraction. Exponents, like let's say a to the x, have log base a. So every operation has an inverse operation, and for differentiation, this is going to be called integration. Now, I'm just going to say that outright, but we don't actually quite know that just yet. And to know this, we're going to have to use, well, I'll talk about the actual definition of the integral in just a little bit, but let's assume that, well, let's not assume, let's just say outright that integration is supposed to be just the area under the curve. So we define f of x is equal to the integral from a to x of f of t dt. In this case, so all this is saying is that if we have a function on a y-t plane, where y is a function of t, and we had a and a b value, let's say that f of t, or y, is going to be continuous on a to b, or actually, this can be closed brackets. A can be included in this. So we'll say that f of t is continuous on a to b, and x is somewhere in here. That's what this is saying. We are going to try and say that, say, this is a somewhat not great looking graph, but this is just saying that this integral, we are assuming that integration is just going to be area under the curve. We can say that this is the area under the curve from some value x on this interval of a to b for this function of t. And now, the object of this proof is to prove that integration is the inverse of differentiation, that there is some inherent connection between the two. So we're going to have to use the definition of the derivative. So let's do so. We have f of x. If we were to do the derivative of this, we'd have f prime x is equal to the limit as h approaches 0 of f of x plus h, or let's use capital letters to keep our notation consistent, f of x plus h minus f of x all over h. And now, we're saying that if we have this input, x, and our output is going to be this integral, if we had x plus h as our input, our resulting integral will be the integral from a to x plus h of f of t dt. Now if we look back at a graph, I'll just kind of sketch it out. This is y, this is t, and let's say this is a, b, x. We're saying that this is x plus h. Let's draw some squiggle. And this is the area under the curve from x to a, or from a to x. And then this, all of it, is going to be the area under the curve from a to x plus h. So when we plug in our x plus h into the input, our resulting output will look a little bit funky. We're going to have the limit as h approaches 0 of the integral from a to x plus h of lowercase f this time, f of t dt minus, and we're just going to plug all of this back in for f of x right there. So we're going to have the integral from a to x of f of t dt. Again, we don't actually know whether these operations are connected. We're just going to try and prove that. The only thing that we know as of this point is that integration is area under the curve from a to x, or this is the area under the curve from a to x. So from here, let's draw back our fraction bar. We're going to have all of this is over h. And now we can simply modify this a little bit. So I'm actually going to draw this out to make sure that these ideas are communicated properly. Let's again say this is y, t, a, b, this is x, and then this is x plus h. Now if we have this function, y equals f of t, and we say that this is the area under the curve from a to x, and this is the area of the curve from a to x plus h, then if we were to subtract this, I'm not drawing this perfectly because I can't, well, I don't know how to switch colors efficiently, but we have this area that is subtracted from this area, which should leave us with just that area, right? And again, we said that this is simply area under the curve, so the integral from a to x plus h of f of t dt minus the integral from a to x of f of t dt should be equivalent to the limit as h approaches 0 of the integral from x to x plus h of f of t dt all over h. And that's just how we looked at this function. We said that from here, if this is the area under the curve, we can take out this integral from x, from a to x, and if we take that integral from a to x out of this integral from a to x plus h, what we're going to be left with is just from x to x plus h. I know that's probably not illustrated super well, but if you just kind of like think about it a little bit, I think it makes sense. We're just going to find the area of a curve, area under the curve of some interval, and then there's a subinterval of a smaller area under the curve. So if you were subtracting that area from the other area, you're just going to have what's left, which is the integral from x to x plus h. And now from here, we're simply going to take out that 1 over h. We're going to have the limit as h approaches 0 of 1 over h times the integral from x plus h, or not from x plus h to x, from x to x plus h, f of t dt. And now I'm going to use something that we might have seen before. I'm not sure if I actually talked about this in my derivatives video. I might need to talk about this in my derivatives video because this is particularly important for calculus students, but the mean value theorem of, at least for definite integrals, states that there exists, that backwards e is just there exists, a c such that x is going to be, well, x to x plus h has c within it, or like, you know, if x to x plus h is some type of interval, then c has to be in the value, then f of c times h is equal to the integral from x to x plus h of f of t dt. Now, this might seem like a bit random. We will talk about this mean value theorem of definite integrals, and probably we are going to talk about the mean value theorem of derivatives as well, but that might have to be in the latter half of this video. Just for now, we just need to know that this is a theorem that exists, and yeah, it's just saying that f of c is equal to f of c is going to be equal to 1 over h times the integral from x to x plus h of f of t dt. Now, this is a bit abstract to kind of think about, but I think maybe if I illustrate it, it might be a little bit easier to see. I'm going to ignore the a's and b's right now. We're just going to focus on x to x plus h. So again, this is t, this is y. Y is a function of t, so y equals f of t. And then we say that this is x plus h. This is the curve, or the area under the curve. And then c is going to be the mean value, or the average value, on this interval. And now, the average value, since this is the mean value theorem, this has to be the mean value on this integral, or this definite integral, which again, at this point, we still think is only the area under the curve. So the mean value on this area under the curve is just going to be the area divided by the length of this base. So x plus h minus x is again going to be h. So we have the length, or the distance between x and x plus h is h. So if you divide this area by h, you should just be able to see what the mean value would be. Like if you had, say, a triangle of length 4, you should be able to divide, let's say 2 times 4, you should be able to divide 8 by 4 into 2, and then say, if this is an xy plane, that x equals 2 should be where the average value lies, right? I think that just kind of makes sense. Once you have this area under the curve, if you divide that by the length of the base, you should be seeing what the mean value is going to be. And yeah, from here we're almost done. Again, remember what we said f prime x was equal to. Let's rewrite that. We said that f prime x, after all of our manipulation, is equal to the limit as h approaches 0 of 1 over h times, I don't know, write it like that, from the integral from x to x plus h of f of t dt. And yeah, this is looking awful similar to that, but we're still gonna have to kind of think about this. So if c is supposed to be some arbitrary x value, we can say that as c approaches x, h is gonna approach 0. I think that just kind of makes sense. If f of x is supposed to be the kind of like average value of some, point on this definite integral, then you want this in this interval from, I'm saying integral and interval a lot, but if f of c is supposed to be an x value, and you are trying to make this integral as precise as possible, we're going to have to constrict our interval from x to x plus h as much as possible. And whenever we're trying to constrict an interval, I was talking about this in our derivatives video, whenever we're constricting an interval, we want our h to approach 0. So from here, we say that f of c approaches f of x. Again, we're just going to plug in x for c, and then this will also be as h approaches 0. Again, we're just plugging these ideas back in. So now, let's write out what we have talked about. We said that f prime x is equal to the limit as h approaches 0 of all of this, right? But we also said that this was equal to f prime c, where, c is the x value of the average value of that, like, area under the curve. So we have this is the limit as h approaches 0 of f of c. And then from here, we simply plug in, not plug in, we said that as h approaches 0, f of c approaches f of x, which means that f of x, or if you have f of t dt, is going to be the antiderivative of f prime x. And this only works because our function is differentiable, which means it has to be continuous. So yeah, this kind of tells us a lot. If a function is continuous, it is going to be integratable. I'm not sure if that's the correct way to say it, but we can integrate it. And yeah, if a function is differentiable, it has to be integratable. And that's an important idea, but I'm hoping we can see some of these connections already. F of t dt, we said that y is equal to f of t, but since we use x as our value, we can write this as f of x, which means that if f prime x is equal to f of x, then we're just going to use this indefinite idea, or this opposite, well, it's not opposite, but it's just, we're using the definite integral, notation, but in a different way. So it's not defined, there's no interval, but we're going to say that if f prime x equals f of x, then the derivative of f prime x, that antiderivative, or that integral, will be equal to f of x, which is an important idea. What we're essentially saying is that differentiation and integration are opposite. They are inverse functions of one another. So whenever we have a integral to do, we simply do the opposite of the derivative. That might make it a little bit harder to prove certain ideas, because it's usually more about memorization, but we can still always, find proofs for these things. But yeah, that wasn't like the best proof of why why the integral is considered the antiderivative, But I hope it does show at least some of the thought processes behind that and how we are going to be using definite integration to see the area under the curve and how to kind of calculate it. Though I'm getting a little bit ahead of myself, we need to talk about the formal definition of the derivative. It's not super necessary to know why this is the formal definition of the derivative. It's more just, you know, kind of like the basis for what we did. I'm only showing it after. I know that doesn't make too much sense, but I'm showing it after because I feel like it's not super necessary to understand. It's just kind of, it's a little bit needlessly complicated, but it is at least interesting in my opinion. So we have the, let me just write down this limit as n approaches infinity of the series when I equals 1, and then this is f of xi times the change in x. Alright? And then we say that if f is defined, I'm gonna kind of use shorthand. If f is defined on a to b, where x is going to be a value, we just divide this interval into n sub-intervals of, xi minus 1 to xi. Let's actually think about that for a second. So if I is some arbitrary value, like say 3.7 something, I could actually be, anything, but it doesn't matter. We have just 1 unit to the left of that to that 3.7. So xi minus 1 to xi, these are just two values that are 1 units from one another, and it's important that these have equal widths. So let's kind of draw this a little bit. Y, x, we have xi minus 1, xi, xi plus 1. These are all 1 unit from one another, and they're also the same, width. If all of this is happening on some interval from some interval of a to b, we're going to use that same idea from that mean value theorem, and we can say that this change in x, let me not erase that. We're going to have the width, or the change in x, between all of these subintervals is going to be b minus a over n. And that makes sense. Like we did in our mean value theorem of definite integrals, we say that b minus a is the length of our total interval, and we have n number of subintervals. So the amount of change in x, just in x, not in y, but the change in x is going to be just the length of the base divided by how many subintervals we actually want. So this is going to be our definite integral. This is going to be the what we are technically calculating every time we do the integral, and this is essentially area under the curve. Now, this isn't really something that you need to prove or to understand how to prove, but it is nice to see where the ideas behind definite integration come from and what area under the curve means in this context. So f of xi is going to be a y value, right? And change in x is again going to be an x value. So I'm going to erase this. You can write this down if you want. Again, this isn't, super important to understand. it's more about the idea that, you know, the definite integral is area under the curve, but it is nice to see why it is area under the curve, provided all of those like ideas. We have n subintervals, we have the change in x is equal to b minus a over n, so the length of the interval divided by the number of subintervals. So from here, we can say that if this is a y value, we can kind of think of it as the height. Okay, I keep writing with my eraser. So we have, if this is an xy plane, we have some fxi is a y value, and then change in x is going to be an x value, right? This can go on. That was actually a really nice extension of the x-axis, but this can go on, and there will always be a change in x for another subinterval over and over and over again. Again, we have some impossible to understand number of n, because we actually have to look at the front of this. We have limit as n approaches infinity of n, which means that on this a to b, we are supposed to have an incredibly large number of subintervals, which means that the width of these subintervals is going to be really, really, really small, right? Let's think about this. If we have b minus a over n is equal to the change in x. This is the length of the interval divided by the number of subintervals is the change in x values. If n is some enormous number, then a regular number divided by an enormous number is going to be a very, very small number. We call this change in x infinitesimally small because it's infinitely small, If n is infinitely large, then change in x is going to be infinitely small. And then from here, again, this fxi is going to be the area, or not the area, but the height of some rectangle, and change in x is going to be the base of this rectangle. So if we multiply the two, I'm hoping that everybody who's watching this video knows that the area of a rectangle is base times height. So if our base is going to be change in x, and our height is going to be fxi, that was a weird looking I. If our height is fxi, then the area of that rectangle is going to be change in x times fxi. And since we have, this is a series, we will actually talk about that series in just a second. Since we have an infinite number of n, that means that we have a bunch of these rectangles. We have rectangles over here, we have rectangles over here, and even though this might look really blocky, we're actually zooming in so much that each pixel will kind of like be its own rectangle. It would look kind of like that. If I knew how to draw straight lines, then it would look somewhat like that. And again, this is obviously much larger because we can actually see it with our eyes, but each of these changes in x, change in x, change in x, change in x, there's a bunch of these changes in x. These are so small that when we calculate f of xi times change in x, we're actually just calculating the area of a impossibly thin rectangle. And then now let's talk about our series part of this. A series is simply the sum of some, sum of some, no, like the sum of a bunch of things. In this case, it is the sum of a bunch of areas of rectangles. So if this was another f of xi times delta x, and this is another f of xi times delta x, that means that when we sum up all of these impossibly thin rectangles, we are actually going to simply get the area under the curve. Um, Again, if we want to illustrate that, we can just kind of say that if this is a curved function, and this is, some delta x, and this is some f of xi, there is a bunch of delta x's out there. And there's a bunch of f of x's, f of xi, f of x I2, not f of x I2, f of xi plus 1, f of xi plus 2, f of xi plus 3, and on, for as much as is possible. There will be an infinite number of f of x values or y values for this infinite number of x values or delta x's. So yeah, I might have made this seem a little bit more complicated than it actually is, but we're saying that delta x is a very, very small change in x, right? And f of xi is going to be the y value associated with that x value. And from here, we simply have so many impossibly thin rectangles that when we find the area for all of them and we add them up, all of it, we'll simply get the area under the curve from that interval of a to b. Remember our original parameters of this definite integral. So yeah, that's why definite integrals are the area under the curve. We say that f of xi is some y value associated with some very small change in x, and every time that you calculate f of xi times delta x, you simply find the area of a rectangle. And since there is an infinite number of these impossibly thin rectangles, when you sum up all of them, you'll simply get the area under the curve from a to b, so along that interval. Again, if that doesn't make too much sense, it doesn't matter that much. I'll try to kind of like sum it up all in one sentence. The definite integral, the formal definition of the integral, simply says that every function, every curve, every function is just a bunch of very thin rectangles all squished together. And if you found the area of those individual rectangles one by one, even though you'd be doing it forever, if you did it and you could somehow do it, then when you added up all of those very thin rectangles, you'd simply get the area under that curve. So yeah, that's the formal definition of the derivative. Again, it's not super important to know, it's just nice to see why it is the way it is. And I think it translates really well into the idea of Riemann sums. Not the biggest fan of these things, I will not lie, but at least kind of knowing the formal definition of the integral might help you in seeing how Riemann sums work. So I am going to use most of these as tables. There might be a way, well, let's see. I don't want to draw tables over and over again. So the Riemann sum is kind of an elusive idea. When we are doing the Riemann sums, we're doing definite integrals, so we don't actually need a table to do these, but you will see some table problems, and I might show an example of them. But let's just describe what a Riemann sum is. There are several types of sums. There are left, right, forget what it's called. Oh, midpoint. Yep. I was about to say middle, and I'm like, that didn't make too much sense. Midpoint, and then trapezoidal. I think for our purposes, that will be more than enough. There might be some, super obscure sum, which you can comment down below, tell me about it. But for our purposes, we're only going to need to know these four. And it's kind of what it sounds like. We said that the definition of the we say that by the definition of the formal, what am I saying? By the formal definition of the definite integral, we know that a definite integral is just the sum of the areas of a bunch of rectangles. So when we're doing Riemann sums, we're actually just going to estimate this using actual calculations. So let's say that we have some f of x, goes on and on. When we are doing left Riemann sums, again, we have an infinite number of, in the formal definition of the integral, we have an infinite number of, I guess I'll just write it all out. We have an infinite number of these n's, or each of these subdivisions. But when we're doing Riemann sums, we have a much smaller than infinity number of subdivisions, so our rectangles aren't going to be perfectly accurate. Let's even zoom in. Let's say that this is some, n, some subinterval. If we were to draw a rectangle from there to there, sure, we can calculate if this is fxi and this is some delta x. We can do a, definition of the integral type sum of rectangles, but this is a Riemann sum where n is not going to be infinity. N is going to be like 4 or something. So we're not going to have an accurate number of like subintervals. So all of this space is either going to be accounted for, or all of this space is going to be unaccounted for. But, I'm getting a little bit ahead of myself. Oops. So let's write it out. We have, this is some rectangle, right? And this is, f of xi. This can also be f of xi. But if we are doing a left Riemann sum, so I'll just stop being coy and say it outright. Riemann sums are just other slightly worse representations of definite integrals. You have a given number of subintervals, so when you are doing a Riemann sum, you don't have an infinite number of subintervals, so we can actually use our, our like formal definition of derivative so that we can get some kind of a answer, but it won't be as accurate as an actual definite integral. So, just that we are perfectly clear, that formal definition of an integral, it was just to see why the integral is, area under the curve. And our first definition, or not our definition, our proof for the fundamental theorem of calculus simply says why integration is the antiderivative. Now, we're going to use some modification of the formal definition of the derivative. We're not doing antiderivatives right now. We will do them soon enough, but right now we are simply using our formal definition of the derivative in a slightly unique way. If we're given a n, when we have this subinterval from, some xi minus 1 to xi, and we have this n, which is the width in between, a left Riemann sum will go from the left of this rectangle and then drop a straight line down. And a right will go from the right of where this point attaches and then go that way. I'm not being super clear about what I'm saying, so we're just going to go straight into a example. I'm only going to talk about left and right now. We will talk about midpoint and trapezoidal in just a second, but the left Riemann sum is where the xi minus 1, or that first x value, intersects with the actual function on the left, and a right Riemann sum is when that x value intersects, or not intersects, but when that x value meets the function from the right. So let's use the first practice problem that I see when I googled Riemann sums practice problems, and that's going to be a somewhat interesting one. That is the approximate area under the curve, so between the x-axis and g of x, when g of x is equal to 2 to the power of x, and our interval is negative 2, 2, 2. And we have 4 subintervals. Now, our change in x, let's even write down our formal definition of the integral one last time. We have the limit as n approaches infinity So the limit as n approaches infinity of this series with n increments and I equals 1, where we have f of xi times change in x, which again we defined the change in x as b minus a over n, so length of the interval divided by the number of subintervals. Now, since this is a modification of our formal definition of a derivative, we only have 4 subintervals. So we have limit as n approaches 4, and we're only adding 4 things, right? So from here, let's do this change in x idea. We have b is equal to 2, and then a is going to be equal to negative 2. So we have 2 minus minus 2 all over n, which is equal to 4. So 2 minuses become positive, so 2 plus 2 is 4 over 4, which is going to be 1, which means that our change in x is going to be 1 unit. Now, you could write down what this problem is asking for us, but I'm just going to erase that. And let's draw what it is asking. So we have our xy plane. This is just going to be, roughly what y equals 2 to the power of x looks like. And let's say that this is x equals 2, and then this is x equals minus 2, right? If we were to divide this into 4 subintervals, then change in x, or the distance between each of these subintervals, is going to be 1, right? If this is negative 1, that's positive 1, and that's 0. Then let me kind of write these slightly better. If this is these 4 subintervals, and this is negative 1, this is 0, and then this is positive 1, then the space in between, right there, right there, right there, all of these are going to be 1 unit, right? And so change in x is going to be 1 for all 4 of these. And if we are approximating from, let's see what the question asks. Oh, they want us to do a right Riemann sums. This is, let's draw this out. This is going to be where the function has that x value, and then we have where that function has that x value, where the function has this x value, where the function has this x value, and then from here, it's when the function touches the x on the right. So we drop a straight line, and we go down to our subinterval, and we have to go from the right. We do not go from the left, because this is a right Riemann sum, and then we go from here to here, we go from here to here. Wait, no, that's definitely not right. So we go from where the function touches that x value from the right, then we drop another one, and then from that value we go to there, and from that value we go to there. And this is going to be an over approximation. That's an important idea. When we have a function that is increasing, if we are estimating from the right, it'll be over. When we are estimating from the left, it'll be under. That's because if you drop a line from the left over here, 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 when f is increasing, that means that each y value, or each x that comes after, means that the area of a rectangle that falls underneath it will be underneath it. Not sure if I'm making that make sense, but what I'm saying is that if f is increasing, right, when we drop lines from when f is touching on the left to the x value of our next interval, or our next subinterval, when we do that, we're actually going to get a rectangle that falls underneath the curve. And if you do that from the right, when you have a function that is increasing and you go from the right to the left, you're going to have a rectangle that goes over the curve. And this is when f is increasing. Now when f is decreasing, it's the opposite, right? If you have f is decreasing and you draw rectangles, so let's say like from there, if you draw rectangles from the right to this next subinterval, so let's say these are our subintervals of, this is some x and this is some y, right? If these are our subintervals, if we go from the right to the left, we're going to have intervals that look like that, right? And then if we go from the right, we're going to have stuff that looks like that, right? So, yeah, kind of abstract of an idea, but essentially when f is increasing, our right Riemann sums will be over approximations and our left Riemann sums will be under approximations. And when f is decreasing, right will be under approximation and left will be over approximation. Then from here, let's just plug in everything that we've been doing, right? So we're doing the right Riemann sums. Let's plug in y equals 2 to the power of 2, which is 4, y equals 2 to the power of 1, which is 2, and y equals 2 to the power of 0, which is 1. So from here, that means that this value is going to be 4, that value is going to be 2, that value is going to be 1, and then 2 to the power of 0. I already did that. 2 to the power of negative 1 is going to be, I don't know why I keep writing 0. 2 to the power of negative 1, yep, I wrote it correctly, is equal to 1/2, and then, from here we have the y value of this part is 1, y value of this part is 2, y value of this part is 4, y value of this part is 1/2, and now we can start drawing our triangles. I don't know what I'm on right now. It is getting late. We're not doing triangles, we're doing rectangles. Okay? So, now let's do rectangles now. So, we have the sum of 4 subintervals of I equals 1. This can also be seen as xi plus 1. You can write it in proper notation if you like, but it doesn't matter too much for the idea that we want to understand, and that is f of xi. We're going to do it from the right, so we have this is equal to 4 times 1. That is the area of this triangle, again, base times height, plus, because this is a series, plus 2 times 1 plus 0, not 0, plus 1 times 1 plus 1/2 times 1. That'll be the area of this rectangle. 1 times 1 is the area of this rectangle. 1 times 2 is the area of this rectangle. And then 4 times 1 is the area of that rectangle. And that is going to be our 4 increments of the series. And so when we plug all of those in, we're just going to get a nice, let's see, 4 plus 2 is 6, plus 1 is 7, 1 half, we're going to have 7.5 units squared. So we got our correct answer, 7.5. Again, this is an over approximation because f, or g in this case, is increasing on this interval, and we're doing a right Riemann sum. So when we drop a line from this side to the other side, we are going to get a over approximation. And yeah, I think that's relatively intuitive. If you'd like to see more, practice for left and right Riemann sums, you can comment down below. I'll do it, obviously. I have nothing more important to do, but I feel like, Riemann sums, while they're probably important for, passing calculus, I don't think they're super important for understanding calculus or, to do integral calculus that well. So let's talk about midpoint and the trapezoid Riemann sums. So midpoint is kind of what it sounds like. Let's even go back to our y equals 2 of x looking graph. Let's go like that. And let's not give any specific subintervals. Let's say that this is a function, right? And getting a little bit ahead of myself. Whoa, okay. So let's redraw that. This is going to be y equals 2 to the power of x. So y equals 2 to the power of x. Let's draw that like this. And let's say that these are our intervals. I know they're not equally spaced, but it doesn't matter too much. We will say that the midpoint is where the x value to the left and the x value to the right, when you divide that by 2, you find the midpoint, and we will find when that midpoint hits the function. And we will do that for all of these intervals. We'll find the midpoint of these two, midpoint of these two, and from here, we'll just draw an equidistant straight line from each of those points. And already you might be able to see this is going to be a much nicer looking approximation, because half of it will be over, half of it will be under. And Fermi's estimation, that's kind of the idea that if you have some pretty egregious overestimations and some egregious underestimations, you'll eventually get kind of close to the correct answer. There was a really nice experiment that he did involving some nuclear bombs or something, and I'm not sure if I'm telling this story correctly, but Fermi, for some reason, put pieces of paper near the near some type of explosion, and he was trying to see how that paper will move and how far it will move. So in his calculations, he had some very severe overestimations of where they would go, and some very severe underestimations of where those papers would fly. And when he did some, math magic to get to his actual estimation of where they were, the papers were very close to, where he thought they would be, because his overestimations and his underestimations balanced out. So with Fermi estimation and with midpoint Riemann sums, I know I just went on a bit of a tangent, but with midpoint Riemann sums, it's the same idea. When you have a midpoint between these two intervals and you drop equidistant lines between those two intervals, it's a lot easier to calculate. So yeah, let's do that. Let me find a practice problem. Alright, so I found a somewhat interesting looking one. I'm not sure if I can actually do this correctly. Okay, it's gonna be a bit of a drawing one. So, I'm just going on Khan Academy and like picking the first midpoint sum problem I can see, and this one does require me to draw, so it's not gonna be, the greatest example because I'm not a great drawer, at least of these graphs with my finger. So, let's say that this is some function h of x, and we are trying to estimate from 0.5 to 3.5 with three equal subintervals. So let's do b minus a over n to find what we are multiplying everything with. So 3.5 minus 0.5 over 3. So 3.5 minus 0.5 is going to be 3 over 3, so that's going to be equal to 1. So we are going to have one subdivision each, and I'm just going to kind of say what the values are. So h of, let's like write these down, 1.5, and then this is 2.5. So whenever we do midpoints between these 0.5s, you could, actually, for practice's sake, I am going to kind of, do this out, even though in my head I know that 0.5 is equidistant to 0.5. So when we are doing a midpoint Riemann sum, let's say we have, I'm not going to write our formal definition again, but we're going to have the kind of, let's say, sure, we're going to say the integral from 3.5, or from 0.5 to 3.5 of h of x approximates roughly to the 1.5 minus 0.5 over 2 times f of that value, right? So let's, we are going to just kind of do that in our head. We know that 1.5, not 1.5 minus 0.5, 1.5 plus 0.5, so 1.5 plus 0.5 is 2, over 2 is 1, so we're going to do f of 1, or not f of 1, h of 1, excuse me. We have h of 1, and then plus we have to do 1.5 plus 2.5 over 2. Again, we're trying to find the midpoint between these two, between these three subintervals, times f of 1.5 plus 2.5 is 4 over 2 is 2, f of 2. And then this is also going to be plus 2.5 plus 3.5 over 2, again, 2.5 plus 3.5 is 6, over 2 is 3, so we're going to be multiplying this by f. I don't know why I keep defaulting to f. It is h. So, times h of 2 times h of 3. And then from here, we can actually kind of draw it. So if this is 1, this is 2, and this is 3, when we draw the x values from there, we are going to, just have them kind of just be there, Like, when that midpoint hits the function, we're going to have equidistant drops between those two intervals. So from here, I can't, well, I could draw exactly this, but this was not drawn by a human. I'm just going to tell you what these values are. So, yeah, actually, that was inaccurate on my part. Wait, no, what am I saying? Okay, yeah, no, that wasn't correct at all. When I was doing that 1.5 plus 0.5 over 2, that's not being multiplied. In fact, I don't know why I wrote any of that. That was completely incorrect. 1.5 plus 0.5 over 2 is just how we are getting to f of 1. And using our formal definition of a derivative, we're just going to be doing fxi times delta x, which in this case is going to be f of 1 times our delta x, which again we said it was 1. So this is f of 1 times 1, f. So I know it's h, but I'm going to keep writing f because I don't know. So f of 2 times 1 plus f of 3 times 1. Yeah, I don't know what that was about, but we know what our delta x is and we know what our f of xi is, so we can just plug that into our original formal definition of a derivative, of an integral. And so f of 1, or h of 1, is, for this function, 3. Again, I could, draw this correctly, but it's not super important. And then f of 2 is equal to 1, 1. And then f of 3 is equal to 2. So 3 plus 1 plus 2 is equal to 6. I didn't write those times 1s because anything times 1 is just going to be anything. So, yep, and we got that question correct. Now let's go on to some trapezoidal sums. Oh, and rather nicely, it has given us a table-based problem to solve. So yeah, I know I didn't explain that midpoint sum as well as I should have, but it doesn't matter too much as long as you understand that we are finding the midpoint, or the average between those two values of any subinterval, and then we just do f of that value, or you plug that into your function, and then you multiply it by the change in x, or b minus a over n. And now our table that we're given is x and f of x, and we have 0, 3, 6, 9, and we have 8, 6, 3, 4. And we have 3 subintervals, so we're going to have b minus a, so 9 minus 0, over n, which again is going to be 3, so 9 minus 0 is 3, over 3 is, 9 minus 0 is 9, over 3 is 3, and then we have the trapezoidal sum. And that's kind of what it sounds like. I'll just draw this out using 2 to the power of x again. With these equal subdivisions, we could draw rectangles. We could do left Riemann sums, we can do right Riemann sums, but those are triangles, and they're not really showing how the curve acts too well. If we draw a rectangle, not a rectangle, if we draw a trapezoid between these values, we actually get a much better idea of what's happening under the curve. Obviously, trapezoids aren't curves, so trapezoidal sums are also not perfect, but we simply add the height over here. We'll call that, well, this isn't really the height, this is actually the base. So area of a trapezoid is going to be base 1 times, base 1 plus base 2 times height over 2. So you're going to add this length to this length, divide by 2, and then multiply by height, so width in this case, because these trapezoids are on their sides. So from here, let's draw our x f of x. Let's say that this is 0, 3, 6, 9, and then, this is 8. Let's draw the y-axis first. 8, 6, 4, 3. I know it's not, correct, but it gets the job done. 0 is 8, 3 is 6, and then 6 is 3, and then 9 is going to be 4. So from here, when we draw these trapezoids, it's going to look kind of like that. And if there were some curve, that went like that, then we'd actually have a pretty good estimation of the area under the curve. So trapezoidal sums and midpoint sums are usually going to be the most accurate in telling you what the area under the curve is without using a definite integral. So let's do this using this table. Now we have base 1 over here and then base 2 over here. So base 1 is going to be 8 plus base 2, which is going to be 6, all over 2 times the width, which we said was 3. For all of these, it's going to be 3, 3, 3, so times 3. And then we again have to add. We have base 2, this will be base 3. Base 2 in this case is going to be 6 plus 3, all over 2 times 3. And then from here, we will have 3 plus 4 over 2 times 3. So 14, or 8 plus 6 over 2, which is 14 over 2, which is 7, times 3, which is 21, plus 6 plus 3 over 2, so 9 over 2, which we can't do anything about, 9 over 2 times 3, which is 27 over 2, and then 3 plus 4 over 2, which is 7 over 2, times 3, so 7 times 3 is going to be 21. So we have, oh, wait, sorry, 6 plus 3, 27, 7, 21, so we're going to have 48 over 2, I think. Let me make sure I didn't do something embarrassing. 9 over 2, 7 over 2, 8, 24. Yep, 24, and then plus 21. Let's see. 24 plus 21. That's going to be 35. Oh, sorry. Not 35. It's going to be 45. Should probably write this out. We have 21. So 14 over 2, 7 times 3, 21, plus 9 over 2 times 3, which we said was 27 over 2, and then 7 over 2 times 3, which is 21 over 2, so 21 plus 27 is 48 over 2, which we said would be 24. So this is going to be 45. And let's put that in. Yep, we're correct. So yeah, that was trapezoidal sums, formal definition of the integral, midpoint sums, left, right, Riemann sums, proof of the fundamental theorem of calculus, why definite integrals are area under the curve, why integration is the inverse of differentiation, and yeah, in the next half of the video that I'm going to probably film tomorrow, I'm actually going to do some examples. We're going to do some U sub, we're going to do some improper integrals, we're going to do actual anti-differentiation, maybe even show some proofs, and yeah, it's going to be a fun time, but I'm hoping that the ideas are coming through on this one. We are just trying to understand. This is the most important thing. Definite integrals is just area under the curve, and integration is the opposite function of differentiation. Those two ideas are the most important ideas, and those are the fundamental ideas of calculus as a whole, of at least integral calculus. So, yeah, again, when we are doing integrals, we are doing the opposite of differentiation, and by the formal definition of the definite integral, that phrase has been tripping me up a lot. But by the formal definition of the definite integral, we know that a definite integral is just the sum of some infinitely many impossibly thin rectangles. So when you add these areas all up together, you'll just get area under the curve. And yeah, in the next half of this video, I'm actually going to evaluate some integrals. So look forward to that, even though when I film it, I'll have been done. So yeah, I'm not going to do an outro because, this is still halfway through. But bye.